Okay, now on to our second clue, the second fundamental principle of cosmology. This comes, like so much of astronomy, from the study of spectra.
Ah, a spectrum. So if we remember, a spectrum is what happens when you spread the colors of light out into the colors of the rainbow, and we assign each color a wavelength. Remembering blue light and ultraviolet has short wavelengths, and infrared, so we're going to have green, yellow, orange, red, infrared as you get to longer and longer wavelengths, and that's the wavelength of light that you're going to measure. And we measure it in angstroms, which is 10 to the minus 10 meters per angstrom. So they're very, very short wavelengths.
What we plot is the amount of energy at each wavelength. And so you can see these wavelengths have a lot of energy, and these wavelengths down there don't have very much energy coming out at that particular wavelength.
And so when you see a spectrum like this, it's actually a mixture of two things. Part of it is because we're looking at a galaxy in this case, full of stars, and the stars are hot, and hot things glow, just like if you really turn, for example, your stove top up really, really hot, it'll start glowing red. That's because it's hot. But then there are these little narrow lines, absorption lines, and sometimes there's emission lines, and that's due to the atomic transitions of each element. They have these places of energy motion between of the electrons through different levels, and those show up at places of color. And so, for example, hydrogen has very specific lines. For example, at 65, 63 angstroms is one of the big lines of hydrogen, H alpha. But then things like sodium, magnesium, various molecules, calcium, all have different things.
Yeah. So this is very familiar to any astronomer, and we would look at a spectrum like this and read off which elements are there. Now that's all well and good, but the strange thing is, this is a key observation, is that when you look at a far away galaxy, you see a different spectrum from a nearby one. So here's a spectrum of a nearby galaxy, and now let's look at a far away one. And you can
so
see
the
the
red
change.
one is the distant one, okay.
And it looks the same, but shifted. Red shifted, moved to a longer wavelength. What you find is that every dip or peak or bump in the spectrum, every emission or absorption line, has had its wavelength increased by a constant ratio. And that ratio is called the redshift and written for some unknown reason as Z rather than R. And it's given by the shift in wavelength divided by the wavelength you'd expect in a nearby galaxy or in your laboratory. So what's going on here?
Well, we know that waves get shifted by the Doppler shift. So we hear that in sound. When a police car goes by you, the sound waves get shifted and compressed and stretched, and the pitch changes. Light's a wave, so that same effect's going to happen. So one can use the redshift to measure velocity. So it's when we see a redshift, it's like the objects are moving away from us. And to first order, that velocity can be calculated as the ratio of the shift of light is equal to the ratio to the speed of light.
Yes, this is an approximation valid for speeds much less than the speed of light, but the galaxies we're talking about are like that. So what it's telling you is if the lines have been shifted by 1% longer wavelength, means whatever is producing them has been moving away from us at 1% of the speed of light. That's a redshift of 0.01.
And so a galaxy that's been shifted by this much, well, that's a big shift. So that means it's moving, apparently, at a good fraction of the speed of light. Now we're going to see that maybe it's not actual motion, but it's sort of apparently moving.
Yeah. And it turns out that almost every galaxy is moving away from us. There are one or two very nearby galaxies that aren't, but almost every galaxy is moving away from us. And if you plot how fast they're moving away from us against distance, you get this plot. What we're plotting here is how fast they're moving away from us. You can see that's 10,000 kilometers a second, 30,000 kilometers a second.
That's 10% of the speed of light if it's a velocity.
Yes.
And then we measure distance, and we can see there's a one-to-one correspondence. The further away you go, the faster the motion.
And this is known as the Hubble Law, and it parameterizes the velocity is proportional to a constant, Hubble's constant, which is about 70 kilometers per second per megaparsec, times the distance.
So 70 kilometers per second per megaparsec means if I'm a megaparsec away, I expect to be moving with a velocity of 70 kilometers per second.
Away from us.
Yes. So, but away from us. Now, everything is moving away from us. This is something that Edwin Hubble discovered in 1929. Now, if everything's moving away from us, Paul, that seems to violate the Copernican principle, e.g., we're no place special. It seems like we are a special place. We're this place that everything's going away from. We're a very unpopular place in the universe.
Yeah. let's say you're living on some distant galaxy a billion light years away, the universe, as we've just said, may look uniform,
Yep.
but they'll be able to tell, hey, everything's moving away from that point. That point must be the worst place in the universe or something, but anyway, special. But it turns out that actually that's not quite the case. I mean, show a little calculation here. Now, this is using vectors. If you're unfamiliar with vectors, we'll put in a link for you to go and remind yourself about this a bit. But this is the vector form of the Hubble Law equation. What it's telling us, this is us, we're on the outskirts of this galaxy over here, and we've got two other galaxies, I called Galaxy A and Galaxy B over here. And what we said is the velocity is equal to a constant times the distance. But these got a little arrow over the top, which means they're vectors, which means that the velocity is in the same direction as the distance and proportional to it.
Right, so vectors, remember, are how far and the direction, typically, is how we can think of them.
So this galaxy is relatively near, so it's got a relatively small velocity, and the velocity is in the same direction as the displacement vector.
Right.
This one's further away, so it's got a bigger velocity, and once again it's in the same direction, and that's simply writing down in mathematical form, everything's moving away from us. The further away they are, the faster they're moving.
And so what you've stated here is Hubble's law, saying the direction and the distance is the same, so that all makes sense to me. It just says that direction we have one answer, that direction we have another answer. So it's just like we just shown with direction added. Okay?
But where this vector thing becomes very useful is if you now ask, okay, let's say you've got aliens living on this galaxy here, what would they see? Now if they look back at us, we would appear to be moving away from them with equal opposite speed. But how about this one over here? What would they see for this other galaxy over here?
Okay.
So the first thing they can ask is, what's the distance, the vector displacement from galaxy A to galaxy B? So that's what's the vector from there to there. And that is simply xb minus xa, vector sum.
So that's the
So that's,
vector
you
arithmetic.
go minus xa plus xb, and that gets you from there to there.
So that would be that arrow. Yes, okay, so good.
So that's how far away galaxy B looks from galaxy A.
Yep.
But then we look at the velocity of galaxy B with respect to velocity A. And once again, the same thing applies. You've got the change in the relative velocity is equal to velocity B minus velocity A. So if you go back, it's got this velocity minus this velocity. It's going to tell how that thing appears to be moving from its point of view.
Okay.
So if you do that calculation, we know that the relative velocity is velocity B vector minus velocity A. But we also know from the last slide that velocity B is h0 xb and velocity A is h0 xa.
Ah.
And so if we take the h0s outside, it's just h0 times xb minus xa, which we just set up here as delta x.
Ah, so it's the distance times the Hubble constant.
Yeah, so what they're seeing is the velocity on the aliens on galaxy A are seeing that the velocity of galaxy B relative to them is just equal to the Hubble constant times the distance relative to them. Just what we see on Earth.
So that means what we've just shown using mathematics, and we've literally proved, is that if we see this Hubble law, everyone sees exactly the same Hubble law. They see the same thing to us and to this other galaxy. We all see the same thing.
Yeah, so in fact, this is perfectly consistent with our homogeneous uniform universe, the Copernican principle, because not only do we see galaxies uniformly, but wherever you are, you see everything moving away. So, how can you work out where the real center is?
Ah, well, I guess we're going to have to think about general relativity this, but it strikes me that if we think of the universe literally seems to be the further away, the faster the motion, so that means the universe is expanding. So let's do a balloon analogy. So let's just think of the universe as being the surface of a balloon. I'm going to put little dots on it, and as I blow the balloon up, every dot, which is a galaxy, is moving away from every other dot. So the galaxies are expanding away from each other. And the further away you are, the faster the motion will be as I blow the balloon up. So I sort of get Hubble's law. But where's the center? It's the center of the balloon. And what was that? That was when I started blowing the balloon up. So the center would be like the moral equivalent to the Big Bang, when you started blowing the universe up.
Yeah, because we can't really tell where the center is, because you can never actually measure if you're moving. All you can measure is you're moving relative to something else.
Yep.
Another analogy would be like baking a bread. Let's say you had a sultana loaf and you bake it in the oven, and we'll have sultanas as galaxies and the dough is transparent. As it gets
For people
bigger,
not from Australia, a sultana is a raisin. So it's raisin bread or sultana bread, yes.
okay, so anyway, small black things inside your bread, doesn't really matter what they are. And as the bread gets bigger and bigger, it carries them all apart. And so every sultana think, hey, every other sultana is moving away from us. Unless they can actually look outside the loaf into the oven, they can't really tell which one's moving. Likewise, for your balloon, if they look outside their sheet of balloon, they can see where the centre of the balloon is.
Yep.
We're talking about a three-dimensional universe. We can't see outside it. So here's my attempt to simulate this. So these tastefully coloured spheres are galaxies, and they're all moving away from each other.
They're all moving away from us, and they're getting smaller because they're getting further and further away. So we're literally embedded in this universe. And if we ask ourselves, well, where's the common center? The common center is right at the beginning of when we started, when we are all crammed into the same spot.
So from where we're sitting here, it looks like everything's moving away from us, but if we were actually on that dot or any dot, they would see exactly the same thing. So they can't really tell. So those are our two clues. We seem to have a universe that looks the same from any point of view,
Yep.
and it's one that's everything's moving away from every point.